Hello, and welcome to Where Music Meets Science. My name is Scott Laird, and I'm a music instructor at the North Carolina School of Science and Math. Today, we will be introducing the term frequency and begin to relate the numerical information of frequency to the musical knowledge that you already have. Following today's lesson, you will have a working understanding of the term frequency, you will know the various parts of a sound wave, and you will be able to calculate octave relationships using your knowledge of frequency. So, without any further delay, let's begin.
Anytime you listen to music and sounds, I'm sure that you are aware that there are high-pitched sounds and low-pitched sounds, and many sounds in between. Great composers write music that has many pitches, ranging from high to low, and that keeps the music interesting. Many musicians choose their instrument based on the musical range of that instrument. That is, how high or low that instrument will play. One person may like the sound of a tuba, or string bass, while another may be drawn to the higher sounds of a flute or a viola. All of these various pitches are a result of sounds that are different frequencies. So, another way to think of pitch is to think of frequency. If an instrument has a high pitch, then it has a high frequency. If an instrument has a low pitch, then it has a low frequency. But the question remains, frequency of what? And how can it be measured? Well, here is where the science comes in. Sound occurs when air molecules are forced together. After being forced together, they then expand farther apart, creating a wave-like motion of air. Look at the cone of a stereo speaker as it is playing music with a loud beat. Notice how the speaker pushes out with each beat. This compresses air molecules and begins the wave-like motion. Here is another illustration of how it works. Air reacts in a manner that is very similar to water when a pebble is dropped into it, creating a series of waves that move out in a circular motion. Think of the water as the air and the pebble as the sound. The sound waves move out from the sound source in all directions, getting quieter as it gets further and further away. A small pebble can represent a high frequency or high pitch. It creates small waves that are very close together. A large rock can represent low frequencies or low pitches. It creates much larger waves that require much more space to develop. So, we can tell that the speed and the size of a wave relate to that wave's frequency. Also, we have learned that frequency is another term for pitch. But let's dig a little deeper. Let's look at the diagram of a sound wave. This is a diagram of the pitch A. It is the A above middle C on the piano. It is also the pitch that an orchestra traditionally uses to tune the instruments. Orchestras around the world tune their instruments to the pitch A. This is also often referred to as A440. 440 is the number that we're interested in today. Let's listen to the orchestra as it tunes. To unlock the secret of the number 440, let's go back to a diagram of a sound wave. This diagram represents the pitch created by a violin playing the tuning note A440. In order to unlock the secrets of the diagram, we must zoom in on the wave, just as if we were looking at it under a microscope. Now we are looking at a very small portion of that sound wave. We said earlier that sounds are created when molecules of air are forced together. The rise in the wave represents the time that the molecules are forced together. The fall of the wave represents the molecules pushing apart. So, the y-axis is air pressure. You will notice that it happens over and over. This takes time. So the x-axis represents time. One complete vibration of a wave is known as a cycle. And this is how we begin to relate these pitches to numbers. Can you guess how many complete vibrations or cycles an A440 goes through in 1 second? The answer is in the name of the pitch. If you guessed 440 cycles per second, you were absolutely correct. This single vibration actually occurs 440 times in 1 second. This is the wave's frequency, the number of cycles or waves that occur in 1 second. Let's look at how fast that really is. Anytime we hear that pitch, the A above middle C on the piano, it is the frequency 440 cycles per second. Let's listen to a few different instruments playing that same pitch or frequency. Another name for cycles per second is hertz. So we might say that you have just heard several instruments playing a pitch that is 440 hertz, or Hz. So, to more completely define frequency, it is cycles per second, or hertz. Now, let's take a look at some instruments that tune to pitches that are closely related to A440. First, let's listen to a cello tuning. Is the pitch that the cello is playing higher or lower than A440? If you answered lower, you were correct. In fact, it is 1 octave lower than the violin A. Let's take a look at the diagram of the pitch that the cello played. After seeing both pitches as diagrammed, can anyone guess the frequency of the cello? If you guessed 220, you are correct. When the cellist tunes their instrument, they hear an A440 and play an A220. This is because the cello is a lower pitched instrument. The cello's tuning note is A220 or 220 hertz. Here are some other instruments that tune to A220. Now let's listen to an instrument that tunes to yet another A. Is this A higher or lower than the cello A? If you said lower, you are correct. If the cello A is 220 hertz, then what is the tuba A? If you answered 110, you are correct. Let's look at a comparison of the graphs of each of these pitches. Let's listen to one more instrument playing yet another A. Using the formula that we have established, can you name the frequency of the bass's tuning note? The bass's tuning note is 55 hertz, or 55 cycles per second. Let's look at each of these numbers and try to find a pattern. Notice that as we move up 1 octave in pitch, the frequency doubles. Can you determine the frequency of the next octave above the violin? If you said 880, then you are correct. Might there be other frequencies that you could be interested in? Here are a few that you may find interesting. This is the lowest open string on an upright or electric bass. This is the lowest open string on a guitar. Let's review all that we have learned today. First, the sound is created by changes in air pressure. Second, these changes occur in a wave-like motion. Third, Faster waves or frequencies represent high pitches. Slower waves or frequencies represent low pitches. Fourth, one complete vibration of a wave is a cycle, and frequency or pitch is measured in cycles per second, or hertz. Finally, octave relationships between pitches are represented by a doubling relationship.
These mathematical relationships between pitches of frequencies can open a whole new world of understanding of music as you begin to use them more and more. In the next lesson, we will discuss the notion of complex waves and the unique sound of each instrument in the orchestra. I hope that you have enjoyed learning about frequency today and how it relates to our lives. I look forward to working with you again in the future. For now, so long from the North Carolina School of Science and Math. Hello, and welcome to Where Music Meets Science. My name is Scott Laird, and I'm a music instructor at the North Carolina School of Science and Math. In our last lesson, we learned about frequency and octave relationships. In this lesson, we will be focusing on the waves that are generated by a variety of instruments and their unique characteristics. In order to do this, let's begin by looking at a perfect wave.
This diagram represents a sine wave. It is a perfect wave. Let's listen to it. Notice that there are no imperfections in the shape of the wave, and it is not very pleasing to hear. This represents a pure, single frequency and really doesn't occur naturally on its own in our world. The sine wave was generated by a computer. It is the frequency 220 Hertz, which we discussed in the previous lesson.
I have chosen this frequency to use today because it's in the middle of the musical range and many instruments can play this pitch.
Let's review the parts of the wave. The high point of the wave represents the place that air molecules are compressed together. The low point in the wave represents the place where they are spaced apart. The y-axis is air pressure. The height of a wave depicts how loud the sound is. Taller waves are louder, shorter waves are quieter. The height or volume of a wave is known as its amplitude. This part of a wave will become very important as we look at the unique qualities of the waves generated by different instruments. If we look at this sine wave in 3D, we see that the only frequency that is represented is 220. There is no amplitude at any other frequency. Now, let's look at the wave that is generated by a cello. Notice that the wave has many more angles and changes than the sine wave. We can see the big portion of the wave moving is at 220, but there are many other changes. What do these represent? Let's take a look at the cello's wave in 3D. Note that there is amplitude represented at a variety of numerical values on the graph. Can you see which frequencies seem to be present? Can you name a few? Is their amplitude the same as the amplitude at 220? Or are they larger or smaller? Note that we are still hearing the pitch A220, but there seem to be other frequencies represented.
This is what we call a complex wave. A complex wave is a sound that is made up of many different sine waves coming together to form the unique sound of, in this case, a cello.
Notice that there seems to be a frequency at 440, 660, and 880 hertz. These numbers, which represent pitches, are very important, and they certainly relate to the pitch A220. Do we know anything about any of these frequencies already? Think back to our last lesson on octave relationships. First, the sound is created by changes in air pressure. Second, these changes occur in a wave-like motion. Third, faster waves or frequencies represent high pitches. Slower waves or frequencies represent low pitches. Fourth, one complete vibration of a wave is a cycle, and frequency or pitch is measured in cycles per second. Finally, octave relationships between pitches are represented by a doubling relationship. In Lesson 1, we learned that 440 Hz and 880 Hz are higher octaves of the pitch A. Octave relationships are represented by a doubling of any frequency. It is important to note that we don't actually perceive these other frequencies that we see in the graph of the cello's note. But these other frequencies and their amplitudes or relative volumes all work together to create the unique sound of every instrument. The frequency that we actually hear is called the fundamental. Note that it is the tallest frequency and the lowest frequency. These other frequencies that show up in a sound wave are known as harmonics. This unique sound of an instrument is also known as its timbre. So, the fundamental and the harmonics that an instrument makes all work together to create its unique sound, or timbre.
Let's take a look at the waves of some other instruments and compare their harmonics.
Here is the graphic representation of a trombone playing A220. Notice the shape of the wave. Again, the big part of the wave appears to be similar to the cello and the sine wave, but the smaller inconsistencies of the wave are quite different. Let's look at it in 3D. What other frequencies are represented in the 3D image of the trombone? Are they the same as the cello or different? Are the amplitudes of the other frequencies similar to those of the cello or different? Is the fundamental frequency about the same amplitude? Which of the harmonics appear to have higher amplitudes? Which of the harmonics appear to have lower amplitudes? Note the clear differences between the cello and trombone waves. All of these differences contribute to the unique sound of the two instruments, or their timbre. Now, let's look at the wave from another instrument. We can note again, as we look at the graph of the wave and compare it to a sine wave, it is clearly not a sine wave. This complex wave, again, is not the same as the cello or the trombone. Let's take a look at these in 3D. Note the similarities between the harmonics in the cello and the trombone and the clarinet. Note the differences. Take a moment to write down one similarity and one difference that you can see. As you can see, each of these instruments has a unique set of harmonics that combine to form the timbre of that instrument.
Even the human voice, in fact, every human voice, has its own set of unique harmonics that come together to form its timbre. Let's take a look at the waves of two different human voices and compare the harmonics.
As you can see, Even while the singers were singing the same pitch, the waves look very different. Each voice has a unique timbre.
So let's review what we've learned in this lesson.
First, we learned about sine waves, perfect waves that really don't occur by themselves in nature. These are pure sounds of a single frequency that are usually generated by a computer or some other tone generator. Next, we looked at the waves generated by a cello. We noted that the wave was much more inconsistent than the sine wave. There was definitely more happening in that wave. As we looked at the 3D representation of that wave, we noticed that there were certainly other frequencies in there, namely 440, 660, and 880. And those frequencies had very different amplitudes than the note or pitch that we hear, the fundamental. All sounds that we hear on a daily basis are made up of a variety of sine waves. These are known as complex waves. The note that we identify is known as the fundamental, and the other frequencies that are in the wave are known as the harmonics. These frequencies all work together to form the unique sound of an instrument known as its timbre. As we look at a variety of waves generated by instruments and voices, we can see that the harmonics all come in a variety of amplitudes. These amplitudes are different in every instrument that we studied. In fact, every voice has a unique set of harmonics that work together to give it a unique quality.
In our next lesson, we will look at these harmonics and try to find some relationship between harmonics and the notes that we understand and work with on a daily basis as musicians. Thank you for joining me for Where Music Meets Science, Timbre and Complex Waves. I hope that you'll join me again soon for the third lesson of our series, Frequency and Harmonics. For now, so long from the North Carolina School of Science and Math. Hello, and welcome to Where Music Meets Science. My name is Scott Laird, and I'm a music instructor at the North Carolina School of Science and Mathematics. In our last lesson, we learned about frequency and timbre, the unique sound that each instrument makes. In this lesson, we will be learning about harmonics and the relationship between harmonics and the music that we listen to every day. In order to do this, let's begin by looking at the notes that make up a major scale. A major scale has 8 tones. Much of the music that we listen to every day is based on a major scale. All styles of music, from pop to folk to classical and even rock and roll, use the major scale as the foundation for their melodies and harmonies. For today's lesson, we will be using the A major scale. This is because in the past 2 lessons, we focused on the note A. However, all of the concepts that we cover in today's lesson relate to all of the major scales.
An A major scale has 8 tones. They are These can be represented with a number as we consider each step of the scale. Now, let's consider some of the important parts of a scale. Certainly, the 2 A's, number 1 and 8, are the most important notes of the scale. They are known as the tonic. and they bear the name of the scale, in this case, A major. The next note of importance is the fifth note of the scale. It is known as the dominant of the scale and is generally considered to be the second most important note in the major scale. Next, we have the third note of the major scale. This note is known as the mediant, and it is the tone that makes a scale major. Lastly, the tonic, mediant, and dominant, or the first, third, and fifth notes of the scale, all work together to form a major triad, or a chord.
Again, we hear major chords every day in music. Now, let's take a look at frequencies and harmonics and how they relate to major chords. Think back to our last lesson on frequencies and timbre.
When the cello sounded an A220, other frequencies showed up in the wave that we studied. Those frequencies are 440, 660, and 880 hertz.
Note that the numbers representing the frequencies are all related. They are all multiples of 220 hertz, the fundamental frequency. Multiples of 220 include the following numbers.
220 times 2 equals 440. 220 times 3 equals 660. 220 times 4 equals 880. 220 times 5 equals 1,100. 220 times 6 equals 1,320. 220 times 7 equals 1,540. 220 times 8 equals 1,760. Look again at the 3D representation of the cello's A220. Can you see the wave at each of these frequencies? We know that A, the tonic note, is 220 hertz. What other frequencies that are shown are the note A?
As you can see, there are 4 A's represented in these numbers: 220, 440, 880, and 1760. But what about the other numbers? First, there's the frequency 660. It is the pitch E. 220, 440, 660, 880.
Note that E is the fifth or dominant note in the A major scale. So, clearly the first 3 harmonics are closely related to the A major scale. They are the tonic, dominant, and tonic notes. Now, let's look at the 4th, 5th, and 6th harmonics.
Using what we know about octaves and doubling, we can name another one of the harmonics. What is 660 times 2? The answer, of course, is 1,320. what is the name of that pitch? If you answered E, you are correct. Now, let's use some reasoning to figure out the fourth harmonic, 1100 Hertz. If you guessed C sharp, you are correct.
Remember that C sharp is the mediant of the A major scale, or the third note of the scale. The fourth harmonic, or fourth multiple of a fundamental, is always the third note of the major scale. Finally, the seventh harmonic is a G natural. Now this may not seem to fit into the pattern of the A major scale. A major has a G sharp. G sharp is the seventh note of the scale.
And while it would take more time than we have today to fully explain the presence of a G natural in this series, I would like you to hear what it sounds like within the chord. A, C sharp, E, G natural. The G natural makes the chord dominant. A dominant chord feels like it should be moving on to another chord.
Now, let's listen to the fundamental and each of the harmonics in order.
Let's review some of the material that we've covered in today's lesson.
First, we discussed the major scale and the important notes in the major scale. We said that the first and eighth step of the scale are the most important tones, and that the fifth and third tone of the scale also serve very important roles. When these tones are played together, they form a major chord, or triad. Next, our goal is for you to understand that there are many frequencies represented in each note that we hear. This group of frequencies, which are multiples of the fundamental frequency, are called harmonics. Next, we considered the numbers that would follow if we listed the fundamental and the first six multiples of A 220. We then looked at the pitch names that are associated with those frequencies. Finally, we found a pattern in those pitches. The first six multiples of a fundamental are the first, third, fifth, and eighth notes in the major scale, beginning on the fundamental. We can draw a close comparison between the harmonics of a note and the major scale and chord associated with that note.
Thank you for joining me today for Where Music Meets Science, Frequencies and Harmonics. If today's topic was of particular interest to you, don't stop here. I encourage you to go to your school library or your community library and continue to learn about frequencies. There are a variety of careers that one might pursue if they're interested in this topic, from physicist to sound engineer to hearing specialist to acoustic architect. A sound engineer uses his knowledge of frequencies and sound to create good sounding recordings and pleasing live sound support in a variety of venues. Here at the School of Science and Math, we had a guest lecturer who uses her knowledge of frequencies to study and predict underwater earthquakes. Architects use their knowledge of frequency to choose materials for buildings. Architects want some rooms to be quite loud and reverberant, while others need to be very quiet. Finally, hearing specialists use their knowledge of frequencies to diagnose hearing problems and to accurately provide recommendations for solving those problems. It has been a pleasure working with you today, and I look forward to the next time we get together.